All right, thank you very much. So as he said, I'm going to talk about type systems. And I work for Khan Academy, where we're working to build a free world-class education for anyone, anywhere. And I work on the mobile team, which means that I spend a lot of time in Java, Objective-C, and Swift, in addition to doing a bunch of JavaScript. So I've seen both worlds, right? I've seen the power and the safety that you can get from one of these compiled, kind of very well-type annotated languages, but I also love JavaScript, and I love the flexibility and the prototyping speed that you have with it. And so I think if we can bring a more formal type system into our JavaScript, then we'll reap a bunch of those benefits. Before I start, here are some things that I like that are cool. If you're interested in any of these things, come talk to me after. I'd love to talk about them. In general, I'm really excited about helping programmers have an easier time of things. We have these computers that are so smart and so fast, but they're so dumb. And there are so many things in our programming workflow that are slow or annoying, or you'd think a smart computer would be able to do this for me. So that's kind of what ties all these things together. But what am I going to be talking about today? First, I want to try and convince you that you need more type errors in your code. And then I'll talk about how to get that, and what changes when you have a powerful type system at your disposal, and how that changes the way that you think about and how you write code. And then I'll just touch briefly on what lies beyond JavaScript type systems. So you might be thinking, no, Jared, I want fewer type errors in my code. But I think you'll find that you actually want more. To start out, I'll just define a few terms. For my purposes, I'm going to say that a type represents a group of things that can be used interchangeably. I just love this GIF of the baby. You've got the square thing, and there are places where it can be used and places where it can't, and sometimes you just throw it out, right? And you'll find that actually in JavaScript we do that a lot. We just kind of bypass all of the things. So in JavaScript we have types. You can think of numbers as a type, so you've got multiplication and subtraction, and regardless of what number you stick in there, it'll at least make sense. It'll give you a reasonable result. Strings have similar operators. You can concatenate strings together. You can take a substring. And we can also think about type that is the group of objects that have a name attribute. So you can say, I have a function. If you give me something with a name attribute, I'll do something reasonable with it. And if in JavaScript, if you do type of x, here are the types that it'll give back to you. It's a small list. Mostly you've got the primitives, and then function and object are just huge. I mean, just about everything you work with is either a function or an object, and JavaScript doesn't really distinguish between this type of object versus this type of object at the type level. So if those are types, then type errors are when you try to use a thing in a context where it doesn't work. And it really depends on the language runtime and your perspective to decide what really is a type error. JavaScript has a very limited view of what type errors are. There's really just blank is not a function and cannot read property blank of undefined. In my example earlier, passing in something that doesn't have a name object where you expect one, JavaScript doesn't care. Here's one of the problems that happens because we have such a limited vocabulary for type errors in JavaScript is that you get the wrong error at the wrong time. In this simple code example, you've got x equals 10, y is x.parent, and you return y.name. Clearly, looking at this code, the problem is that numbers don't have a parent attribute. But JavaScript doesn't complain until the third line, saying undefined does not have a name. Now, you might be thinking, off by one, right? You look at the code, you can see it. But in the real world, it's off by thousands, right? You see this undefined is not a function, and the actual problem, the code change that caused it, is many call stacks away, many files away, and you spend all your time hunting down, logging values, throwing in breakpoints. So you've got one of these, where your code doesn't work. Clearly, there's an error, but the actual problem is so far removed from what JavaScript tells you that you spend a lot of time hunting for it. But even more problematic than this is when JavaScript doesn't give you any errors at all. Right? Here's an example function. You do something, and it expects an argument that has a name attribute, or has a count attribute, sorry. And if the count is larger than 2, then we say it's large, otherwise it's small. And we're passing in a number that clearly doesn't have a count attribute, but JavaScript thinks that's fine. The count is undefined here, and we all know that undefined is not larger than 2, so it'll just return small. And so you're left with one of these, where you look at the page, and there's clearly something going on that you didn't expect. But you don't have an exception to tell you where it's coming from. You don't have a traceback. So again, you're logging out all these variables, trying to figure out where did that, not a number, or where did that undefined kind of creep into the code because of something that in reality is a type error. It's using something in the wrong place, but JavaScript doesn't care. To give it credit, JavaScript's trying to give you the benefit of the doubt, right? It says the programmer's smart. They probably meant to divide 2 by the empty string. And the answer is infinity. This is great. But it really backfires because JavaScript tries to avoid throwing type errors at all costs, you end up spending so much more time debugging. So hopefully at this point you're with me in that we need more type errors in our JavaScript. We need more kinds of type errors so that it'll be more expressive and we'll be able to tell, okay, what is the actual problem here? The first line of defense is actually linters. And you might be thinking, what do linters have to do with types? But they do know about 2 types. There's declared and not declared. And in non-strict JavaScript, this code wouldn't even be an error, right? I've typoed argument, it's Bergman. But JavaScript would say, oh, that's fine, it's undefined. Undefined plus 1 is not a number. We'll just return that. If you have strict mode on, then at least you get an error at runtime. But even there, a linter helps, because it tells you before you run the code that there's a problem. So linters run ahead of time. They're very little work, but they're also super rudimentary. The next line of defense is custom runtime checking. And you've probably run into this, especially if you look into the source code of a well-used library, where the author of the library wants to make sure that clients get useful error messages when they use the functions wrong. Because JavaScript doesn't care about argument length or argument types, the author of the library goes in and checks, is it the right number of arguments? Do these have the right types? Let's say, for example, we've got this greet function that takes a string, a list of strings, and a number. And so the bottom 3 invocations are errors. And if we didn't do anything, they might return just something weird. They might return not a number or undefined, or they might throw, undefined is not a function somewhere down the line. But we want to be nicer than that. We want to be informative to the client about what the problem actually is. And so first we check the length of the arguments. If it's not 3, then we just bail. But we also want to make sure that they give us the right type of arguments. And so, being the defensive programmer that you are, you start adding more of these if statements, more of these errors. And it just gets out of hand real fast. This isn't particularly readable. It's not going to be fun to maintain. And in many cases, you have more lines of code just checking the arguments than you have doing the actual logic. And so unless you are the maintainer of a really popular library where you want to be really friendly to your users, it's just not worth it. So custom runtime checking is very powerful, but it's lots of extra code, and it's only at runtime, right? Your IDE is not going to be able to take advantage of these checks that you've got and tell you beforehand where the problems are. Now, if you're familiar with React, React has this thing called propTypes, which are essentially custom runtime checking done right. It's much easier because they provide all these functions for you, and they do the checks themselves, so it's not cluttering up your code. You just say, this component wants a greeting that's a string, and months that's a list of strings, etc. And at runtime, React will check, was this component called with the right arguments? And it'll do a console.warn if it wasn't. So this is nice. There's not too much extra code. It's nice documentation. You can see you look at a component and you can see exactly what it wants because it's very readable. But again, it's only at runtime, and it only applies to React components. It's not going to work for your other functions. So now we come to the static type checking, which is what I want to sell you on. And I'll be using Flow for these examples, but TypeScript is also awesome and does many of the same things, so the same principles apply. Here's a little primer on what it would look like to add Flow annotations to a function. We've got our sayHello function that takes a name that's a string and returns a string. And these annotations will look familiar to you if you've written any Swift, or Rust, I think, uses a similar pattern. There are a bunch of languages that have these kind of annotations. So we can annotate a function, but we can also annotate variables. We can say the value of this variable ought to be a number. But one of the great things about Flow is that it has very powerful inference. And so most of the time, you don't even have to add any annotations, and Flow will know. Clearly, that's a 10 literal. That's going to be a number. It will also infer from function calls. SayHello returns a string. Greeting will be a string. And actually, in this case, we can just remove the annotations from sayHello because Flow will be able to infer those as well. And I found in the vast majority of the code, Flow already knows what the types are, and I add type signatures just for my benefit so that I can read the code better and it's self-documenting. So here's what it looks like in comparison to the custom runtime checking I was doing before. Right? Much more concise, much more readable. This is what it looks like compared to React propTypes. And you can tell that the folks building React propTypes were very much inspired by static type annotations because they're very similar. So static type checking runs ahead of time. It integrates with your IDE, so you know already what the errors are going to be. There's not too much boilerplate. It applies to everything in your code, and even things you don't annotate yourself. And it's just wonderful for readability. It's so much nicer to go into a big code base that is fully Flow annotated than it is to go into a normal JavaScript code base, and you're looking at this function, and you see that it takes an object, right? A config object is the best. And you have to search around for function invocations to be like, OK, what does this even look like? And it's even better when different invocations pass different things, and so it all looks really hard to track down. So I really like tables because they let me show unequivocally that the thing I like is the best. So take this for what you will. But I think it lays out some of the pros and cons, some of the things you can weigh. At Khan Academy, we've been using Flow on the mobile team actually for over a year. We've got some JavaScript where we tie the native code to an embedded web view. And we really want that code to be rock solid because anytime you're dealing between two different platforms, it can get hairy. And so that is fully Flow typed. And then on the web front-end team, we've been using Flow types for about 6 months. And so out of the thousands of JavaScript files that we have, about 300 or so have Flow types in them. And here are some of the reactions from just within the team, what they think about it. One experience we've had is many times adding Flow types to an existing large file, it finds bugs that were in there, bugs that we hadn't come across or that we hadn't fixed. Our users may have come across them, but they didn't tell us about it. And so that's a really nice feature where it's just like, oh, there's a bug already there. I can just go ahead and fix it. It really helps if you're on a large team. With a bunch of people making changes to a single code base, having Flow to back you up will make it much less likely that you'll wreck things for everybody else. And then, again, it's just a lot easier to read. It's not all good, though, right? Sometimes integration with editors is a little finicky. It's getting better, though, but it can cause you some headaches. And adding a new syntax of these type annotations on top of all the new ES-Next stuff that we're learning can have a real cost for a large team, and so that's something you want to weigh. So far, I've talked about how having type annotations and having this more powerful type system at your disposal will help you debug better. It'll catch bugs for you. You'll be able to refactor with confidence. But I think even more important than that is the way that it changes the way you think. Could I get a quick raise of hands? How many people have used Flow or TypeScript in their JavaScript? Cool, cool. How many would use it again? Awesome. So hopefully you're already sold on this, but you can take these lessons and use that to sell it to your coworkers, to your boss. Because there is a real cost, and oftentimes people look at this, they look at adding type annotations to JavaScript, and they think, you know, we already find bugs on our own. This is going to be a whole lot of extra work, adding all these type annotations, and what will it give us? Right? Maybe we'll find bugs faster, but is it worth the cost? I would argue that from the bug finding alone, it really is worth the cost. But even more than that, it will make your code cleaner and more readable. So that's what I'm talking about here. I'll start out by talking about clever code, and then implicit invariants and implicit state machines, which are very related, and then how writing down data types can improve your code quality. What I mean by clever code, there's this really good quote on the internet where talking about how code is so much harder to debug than it is to write the first time. And so if you're feeling super clever when you're writing code, you just don't have a prayer of debugging it. And that's happened to me a lot, I can tell you. This is kind of what I mean by clever code. In the first instance, we've got a props object, and we want to set the on-mouse down or the on-click to be a function. And you want to do it in one line, and so you've got this little ternary, and you do some string concatenation, and it's awesome. It's actually not super awesome, not very readable, and Flow is going to have a hard time figuring out what the result of this is. It's not going to evaluate your ternary for you. And so this second example is, 4 more lines. It's a 500% increase in lines of code, but really it's much more readable, much more maintainable, much less likely to have bugs in it if you were to misspell one of those strings up there. Another thing that's super common in JavaScript, it was a lot more common a couple of years ago, but it still happens, is when people take advantage of the fact that JavaScript doesn't care how many arguments are in your function or what the types of the arguments are. And so you just go crazy. And you've got these functions that if you pass in 4 arguments, then it's a number, string, callback function. But if you pass in 2 arguments, then it's a configuration object callback function. And if it's 1 argument, then it's just the callback function, and it returns this, so you can chain. It's like crazy to get your mind around. And for one thing, Flow would have a really hard time figuring out what the type is. You would have a hard time writing down the type for that function. But even more than that, as a client of a library, I don't want to have to remember a dozen different ways to call this function. There's going to be one way so that when I'm looking at the use case, I know exactly what to do. So in general, I've found that if some code is hard to type check, it's probably going to be hard to understand. The next way that having a type system in mind helps your code maintainability is with implicit invariants. Now, an invariant is a guarantee, and if it's implicit, that means it's not enforced anywhere. It's not in the code. You'll have it in your mind when you're writing the code, and you might write it in a comment, but nothing is enforcing it. As an example, I'm going to use React for my code here because that's what I like the best, but the same principles apply if you're writing Angular or Ember or Vue. A common thing that you do when you have a component is it depends on external data, so you need to load. And while it's loading, you show a little spinner, and then if there's an error, you show an error screen. Otherwise, you render the happy path. In this case, the happy path is a button that wants you to click it. And the state that we have to worry about is whether or not it's loading, and then an error that's potential error and potential data. Now, the question mark in front of the string and the sum object mean that it's an optional type. So error might be null or a string, and data might be null or some object. Because at the beginning, when you're loading, you don't have either of those. So this is all well and good. until you try and create that onClick handler. And let's say we want to alert the name of the data. And Flow will complain here saying, no, you said that data might be undefined at any time. So you have to add a check. You have to convince me that data is not undefined. And you might be thinking, I wrote this code, I know it's not going to be undefined, because the only way that onClick could be called is if the button is rendered. The only way the button gets rendered is if we have data. How hard is that? But this is an implicit invariant. One way to fool Flow, to get around this, is you just throw a bogus error. And if you find yourself doing that, you probably need to take a closer look at how you're structuring your data, because this will bite you, right? Someone will come in not knowing that that these invariants you have in your head apply, and call the function in the wrong way, render things in the wrong way. And it's actually not very hard to restructure this so that onClick will never be called if data is undefined. You just have to create a child component, make it so that onClick literally can't be called if you don't have data, not that it just won't be called because you wrote it that way. And here's what that might look like, right? We make the contents component that takes the data as props and then has the onClick handler and uses that. And so the way that the code is structured enforces the invariant that you had in your head that onClick would never be called unless you had data. A more advanced example of this is with implicit state machines. Now, a state machine is a thing that can be in multiple different states. An example of this from the Khan Academy mobile app is in the exercises part where you can do math problems. And to start, there's a loading screen where it loads up a bunch of different problems for you. And then you start answering the problems, and you go through. And once you've finished all the problems, then it shows you a congratulations screen that has points, how many points you earned, and any badges that you earned. And the kind of naive way to go about this, to think, OK, what data will I have involved? What's the type of my state object? Is to just kind of list out all of the state that's involved. Right? We've got loading that's a Boolean, problems that is an array, but it's not there at the beginning because we're loading. Answers is also an array, but again, it's not there at the beginning because we're loading. Current problem will be an index, just a number. And points data will load at the very end, so it's optional. And then it'll be present in the final screen. And this is what that kind of state object would look at these various different stages. Right, you've got loading is true at the beginning and nothing else matters, and then answering, loading is false and problems and answers are populated, and current problem is something reasonable, and then finished, nothing really matters except for the points data that we've got. The problem with this state representation, the type that we've created, is that it allows for invalid states. Again, here's the state type, and what happens if loading is false, but problems is populated, but answers is not. And again, you're thinking, as the developer, I wrote the code. As soon as we get the data, I set loading to false, and I populate both problems and answers at the same time. This will never happen. Trust me, it will happen. Right? You come back in a couple weeks, or your coworker comes in, doesn't know what these implicit invariants are that you have in your head, and it breaks. Now, in a language like Swift, this is a structure that we could use, an enumeration that has different cases. The loading case doesn't have any important data, and then the answering case has the problems and answers and the current problem, and then the finished case has points data. In Flow, we can use a tagged union, which is essentially the exact same thing, but it allows us to use normal JavaScript objects to represent the same thing. So there's a loading screen, and then the answering screen with problems, answers, and current problem. And you'll notice here, problems and answers are no longer optional. So we're now enforcing the invariant that we had in our head that if problems is there, answers is going to be there as well. And then the third screen doesn't care about the other data. It just has the points data. So if you're going through and you're creating a component that has a bunch of state and it goes through transitions, and you find yourself making a bunch of things optional. It's probably that you're trying to represent a state machine, but it's not going very well. So consider using a tagged union or one of these constructs to make explicit the invariants that you have in your head. The last thing that having a rich type system kind of pushes you towards is to think about types in an explicit way, right? If you're going to have to write down the types, I've found myself at the beginning of a project thinking, okay, what is the data going to look like? Let's write that down. For a hypothetical blog post app, I think about, okay, what is the post type going to be? And let's write it down. I'm not advocating for a Java style, like create a class hierarchy and a UML diagram. This is essentially the same thing as a database schema. But you can create it for all of your JavaScript data objects. And it makes it easier to think about, okay, how am I going to structure the code? And much less likely that you'll run into errors later on. So these are the ways that having types, having a rich type system in JavaScript will change the way that you think about and write code. But Flow or TypeScript, they're an 80% solution. They have escape hatches out of kind of pragmatism because JavaScript isn't always well formed. It's not always sound. And you add types incrementally, but there are ways to get out of it. As you remember the kid doing with the blocks, you just take off the box. One way that happens is if you're using an external library, by default, Flow will just make everything the any type, which is like all bets are off. In this function, I'm using the _.pick function, and I want to return the name. I've got a spelling mistake, but even if I didn't, I would have a type error because I'd be returning a string when I claim to be returning a number. Even if I fixed the typo, Flow would have no problem with it because I'm using this external library. Now, you can add type annotations for external libraries, and you can add those module definitions, but this is a thing that will bite you if you're not wary of it. And then the other place is when you've got a deadline, you don't want to worry about typing out the types and figuring out what it is. You just say it's any, and again, all bets are off for type inference and type checking with respect to those values. And in our code base at Khan Academy, I said we had 300 some files that are flow typed. About a quarter of them have any types in them. Because pragmatism, because it's hard to type or we don't have time and there's a to-do, type this later. And unfortunately, 80% typed might mean that all of your users see errors. So we've got these compromises in Flow and TypeScript. And I just wanted to touch briefly on what else is out there. Like, what if you want more? And the two things I'll talk about are Elm and Reason. Those are my favorites of the vast landscape, but there are many more if you are interested. And the things that Elm has going for it has really good community, really good documentation. And the build tools and the publishing tools are very well made. But the interop with JavaScript is very restricted in the interest of soundness, right? They want to make sure that to the greatest extent possible, everything type checks. And so they don't have kind of the compromises that you get in Flow. But it's also a fairly young language, and to be honest, I'm very opposed to Haskell-like syntax. Like that might not be a thing for you, but Python's okay. Curly braces are great, and I can't handle the syntax. So Reason is something you might have heard about. It's kind of been developed for somewhat over a year. And it's based on OCaml, which is an incredibly mature language, a really awesome type system. And there's a culture of pragmatism that helps you get things done. Like you can have mutable variables if you need them. You frequently don't need them, but sometimes you do. And the JavaScript interop is really good. So it's much easier to incrementally add reason to your JavaScript code base. And if you're interested in it, it has a native compile target, so you can compile to native. But I'll warn you, the documentation is terrible. OCaml is a very academic language, and they haven't really focused on kind of outward outreach or community quite as much as these other languages. And the reason folks are still trying to get build tooling in a shape that's not terrible. So this is kind of another table. You can find all these slides, by the way, at jaredforsyth.com/typesystemjsdev if you want to go over this afterwards. But again, there are caveats. I think reason is super interesting if you want to go that way. Elm is awesome. Lots of people are using it in production and are very happy about it because they don't have runtime errors anymore. But TypeScript and Flow are kind of the more pragmatic options. If you do want types, but you're not ready to switch to a whole different language. And one more thing before I close. People often ask me about Flow versus TypeScript, right? There's kind of lots of debates. These are my opinions that aren't at all based on the merits of the type system, really. You can see comparisons of, like, this has this feature and this has that feature. But Flow, we chose Flow at Khan Academy because it's good for incremental adoption. We already used Babel and Webpack in our tool chain, and so adding in Flow is easy, whereas TypeScript wants to kind of own the whole system. And that's really nice if you're starting a new project and you don't want to mess with Babel config, you don't want to mess with Webpack. But if you're trying to integrate with a current thing, that can be more difficult. So in conclusion, JavaScript doesn't give us nearly enough type errors, but static type checking can help tremendously. And once you have a rock-solid type system in your tool chain and you get used to it, it'll change the way that you think, and you'll write better code. And if you get frustrated with the 80%, there's more out there. Thank you very much.
That was great. Thank you.
Thanks.
So I have questions. The audience has questions. They also said nice things about your talk.
Oh.
One question I had is, how do tests fit into this landscape where you have a lot more tooling checking your code for you? How do you know what to test? Do you not need tests anymore? Can you talk about that a little bit?
Yeah. You definitely still need tests. There are a lot of tests.
Shucks.
There are a lot of tests that are obsolete if you have type checking, right? In kind of the current JavaScript ecosystem, and also in other, like, more loose languages like Ruby and Python, there's a strong culture of you test everything, and you write a test to make sure that it returns the right type, and you don't have to do that anymore because you have the types that are checking everything. So there are a lot of kind of menial, annoying tests that just go away, which is nice. But
Sure.
you still want to have tests to make sure that the logic is sound, right? Because the type system can't check that.
That makes sense. What would you say to people that have maybe had experience with other type systems and have not liked them?
Right.
A lot of people learn Java in school or as a first language. Java is fine, but some people have criticisms about its type system.
I'm totally with you. I was scarred by Java early on. I now write it professionally, but I was really unhappy with Java for a long time. And Flow is much nicer to use than Java. Because it has all this inference, right? You don't have to write down types for everything. The minimum it requires is adding function signatures for anything you export. But within a file, any functions or components that you have, you don't have to write types for them, and they'll be inferred. And then the other nice thing that Flow has over Java is that the type system is actually more powerful. It's very much inspired by OCaml's type system. And so if you've had annoyances with Java where it's like, oh, I can't really express this, or generics are mostly fake.
Screw it. It's a map of string to string.
Right. Then Flow will hopefully be better for you.
Sure, that makes sense. A question from the audience was, so Flow and TypeScript, they look like great tools, they look helpful, but they're not standards, and you're kind of, it is another language, right? It's a superset of JavaScript, but it's still, you're not fully in the JavaScript camp anymore. So if you're already going to write something that isn't technically JavaScript, why not just go all out and write a compile to JS language? Does that make sense?
Yeah, well, that's where the interop story comes from. With Flow, the only thing you need, if you're already using Babel, then Babel will strip out type annotations anyway. And so all you need to do is install the Flow package and add the Flow comment at the top of the file, and you're good to go. Right? You don't have to convert files over. Whereas setting up a whole new tool chain to get Elm into your project or to get Reason into your project can be a lot of work, and frankly, much more expensive than it's worth, especially if you have a large team. Getting everyone on your team to learn this new language is much more expensive than saying, by the way, like, if you've got colon number, that means it's going to check to make sure that's a number. Sure.
That makes sense. I think this one is a tricky question. How do you type check dynamically download a JSON using Flow? So part of that is like, how do you handle runtime stuff? And the other part is, how do you handle, you see this a lot with like custom fields where people can add new fields to a form or something. And then now you have these extra fields that might be there, but they're user generated. How do you handle really dynamic stuff like that in Flow?
It kind of depends a little bit. One way to take this question is, I'm downloading JSON, but I know what it's going to look like. Or I know that it will fall into one of these three camps. And so then you can do a check, does it have this tag on it, does it have this tag on it? And then you add the flow type to say, now I know that it fits this shape, and I'm going to promise Flow that it looks like this. And then all the guarantees will follow from that.
Sure.
So there's definitely places where you do checks at runtime, and then you hand it over to Flow and say, OK, it's all good.
So there's kind of like this barrier between the dynamic stuff and the Flow code.
Yeah.
That makes sense.
And Flow can actually oftentimes use those if statements that you have to automatically infer, OK, it's of this type as opposed to of this type, which is really handy.
Yeah, that's cool. I think the last question is, what size of projects does this make sense on? Is there a certain size where you say, like, OK, we have X number of lines, so we should really be using a static type system, or is it fuzzier?
I'll tell you that when I start a project, I want to go fast and loose on a side project. And I want to prototype, I want to move quickly. But invariably, there comes a point where I'm looking at the code and I'm thinking, I really wish I'd added flow types to this last week, because I have no idea what's going on.
So the size is like 500 lines smaller than the time you decided to add it.
Yep.
OK, that makes sense. So use a time machine.
That's right. Yeah, I mean, it's nice because you can add things incrementally.
Yeah.
Right? You can mess with something, and then once it settles down, you go in and add your flow types. And periodically, I go through a phase where it's like, I don't want to mess with flow, I'm just going to turn it off. And then I play with things for 2 days, and then I turn it back on and just spend an hour and fix everything.
It's kind of like a spike of crazy looseness, and then
yeah,
that makes sense. Awesome. Thank you so much for your talk. It was great.
You.